Welcome to day 30 of our programming course. In today's session, we will be exploring paradigm-specific language constructs, focusing on how different programming paradigms introduce unique constructs that help developers solve problems in various ways. Programming paradigms introduce specific contrasts that shape how developers approach coding challenges. Each paradigm brings its own set of tools and techniques for solving problems, making it essential to understand these contrasts in order to choose the best approach for a given task. Let's start with functional programming. One of its key features is first-class functions, where functions are treated as first-class citizens. This allows us to pass functions as arguments, return them from other functions, and assign them to variables. Another important construct is map and reduce, which allows us to operate on collections of data. We have we also have lazy evaluation, where expressions are evaluated only when needed, and pure functions, which are functions that have no side effects and always return the same output for the same input. First-class functions allow us to pass functions around just like any other variable. For example, in Haskell, we can define an add function and then pass this function to another function that applies it to a list of numbers. This makes our code modular and more reusable. Map and reduce are higher order functions that are commonly used in functional programming. Map applies a function to each element in a collection, while reduce combines all the elements of a collection into a single value. For instance, in Python, we can use map to double each element in a list and reduce to sum all elements in a list. Lazy evaluation is another powerful concept in functional programming. It means that an expression is not evaluated until its value is needed. This allows us to work with infinite data structures or rely computation or delay computation until absolutely necessary. In Haskell, we can define an infinite list and take only the first few elements without causing any performance issues. Next, let's look at object-oriented programming, OOP. OOP introduces constructs like classes and objects, which acts as blueprints for creating instances of objects. Inheritance allows one class to inherit properties and methods from another, while polymorphism enables different classes to respond to the same method in different ways. Encapsulation protects an object's internal state by only exposing relevant information. In OOP, we define classes that serve as blueprints for creating objects. For example, in Python, we can define a class car with properties like model and methods like drive. We can then create an instance of the class like myCar equals to car Tesla and call its methods like mycar.drive to perform actions. Inheritance allows one class to inherit the functionality of another, while polymorphism lets us use the same method name for different types of objects. For instance, we might have a shape class with a method area and then circle and square classes that implements the area method in their own way. Polymorphism allows us to call area on both objects even though their implementations are different. Logic programming is based on facts and rules. It defines relationships between different entities and allows us to make logical deductions. For example, in Prolog, we define facts like parent Alice, Bob, and then use rules to deduce relationships like ancestors X, Y, parent x, y, which means that x is an ancestor of y if x is a parent of y. Concurrent programming deals with multiple tasks running in parallel. Key constructs include threads, which are independent execution units, and synchronization primitives like locks and semaphores to manage concurrent access to shared resources. Message passing allows processes to communicate with each other, as seen in languages like Erlang. In concurrent programming, we use threads to execute tasks independently. For instance, in Python, we can create a thread to print numbers concurrently with other tasks. Synchronization primitives like locks are used to ensure that threads do not interfere with each other when accessing shared data. Message passing is another critical feature in concurrent programming. It enables processes to communicate with each other by sending messages. For example, in Erlang, we can send messages between processes to coordinate their actions. This approach is especially useful in distributed systems. In conclusion, each programming paradigm offers specific contrasts that shape how we write and structure code. By understanding these constructs, such as first-class functions in functional programming, inheritance in OOP, and message passing in concurrent programming, we can make better decisions when choosing the right paradigm and tools for a task. Thank you for your attention. I would now like to open the floor for any questions or further discussions on paradigm-specific language constructs. Feel free to share your thoughts or ask for clarification on any topic we covered today.